Hello friends, in this session we will solve some numericals on state space analysis. Let's begin. Yes, so now if you see here, obtain the state space representation for a system described by the following transfer function in Jordan canonical form. That is what they are asking. They're asking you Jordan canonical form. Now we need to understand when they are saying that Jordan canonical form, which means yes, there has to be repeated poles or not. Yes, so there are repeated poles. S equal to minus 1 has been repeated twice. Yes. Now, in order to find the Jordan canonical form, what do you should have? You should basically have the poles and you should represent the system, represent the transfer function in the form of a partial fraction. That is what we have seen. So now let us try to do so. Yes, so 2s plus 6s plus 7 upon s plus 1 the whole squared into s plus 2 is our transfer function. If I want to show that in a partial fraction expression, how will I show that? It will be nothing but a upon s plus 1 plus b upon s plus 1 the whole squared plus c upon s plus 2. Am I right? Yes. Now, let us try to find so. If you remember, I had told you one shortcut, right? But now see here, you have got these two poles which are repeating, and we had talked about that yes, the shortcut is not applicable when the poles are repeated. Now, when the poles are repeated in such a case, what to be done? We have already seen that. See, these two poles are repeated, but this is not repeated. No, s plus 2 is not repeated. So, I can definitely find the value of c, right? So, just try to find the value of c. How to find c? Just write this complete LHS. What is the complete LHS? Complete LHS is going to be 2s squared plus 6s plus 7 divided by what? Divided by what? Divided by s plus 1 the whole squared, right, into s plus 2, but except the term which is there below c. So I'm not going to write s plus 2, right? Yes. Now this we have to find at s equal to what? So you please equate this to 0. So you get s plus 2 equal to 0, you get s equal to minus 2. We have seen that. So now s equal to minus 2 you just put there. So what you find here? Yes, you find that it is going to be 2 into, yes, minus 2 squared plus 6 into minus 2 plus 7 divided by what? Divided by 6. What is s? S is what? Minus 2 plus 1 the whole squared. Now if you see, this is equal to what? Yes, it is equal to minus 2 the whole squared is 4. 4 into 2 is 8, right? Minus 6 into minus 2 is 12 plus 7 divided by 1. So you get c equal to 3. This is the value of c. Now you need to find the values of a and b. If you cannot see, shortcuts are very important here. Here you just cannot go like, yes, some people do that. Take this s plus 1 s plus 2 there on the right hand side and all. No need to do that. Just simply put s equal to some number which should not be a number which is already used. What do I mean by that? Already you have used s equal to minus 2, right? Yes. So now please don't use s equal to minus 2. So now in this complete equation, now see, in this complete equation I have to put, so put s equal to 0, let us say, and value of c is already known, so c equal to 3. If I do so, what do I get then? I am going to have 2s squared plus 6s. There already s is there, so it becomes 0 plus 0 plus 7. 7 divided by what? S plus 1. 0 plus 1 the whole squared into what? 0 plus 2. Now next, a upon 0 plus 1 plus b upon 0 plus 1 plus c upon what? C is nothing but 3. So 3 upon what? S plus 2. So 0 plus 2. What do you get here? You get here 7 by 2 is equal to a by 1 plus b by 1 plus 3 by 2. Is that correct? Yes. So if I just keep a plus b on this side and if I shift this 3 plus 2 on the other side, what do I get is a plus b equal to 7 by 2 minus 3 by 2, right? Therefore, what you get is a plus b equal to 2. Let me call this as equation 1. Now, you need another equation as well because unknowns are 2, right? So, let us put s equal to 1 and c equal to 3 in our original equation, right? So, let me put s equal to 1 and c equal to 3 in our original equation, where this orange which I have marked, our original equation, let me put it there. The moment I put it there, what do I get? 2 into 1 squared, because it is 2s squared, so 2 into 1 squared plus 6 into 1 plus 6 into 1 plus 7 divided by s plus 1 the whole squared. So in place of s I have to put 1, so it becomes 1 plus 1 the whole squared. So 1 plus 1 the whole squared multiplied by 1 plus 2, so it becomes 1 plus 2, right? Which is equal to what? A upon, yes, I have s plus 1, so s plus 1 is what? 1 plus 1 plus b upon what? 1 plus 1, s plus 1 the whole squared, so 1 plus 1 the whole squared plus, what is there? C is nothing but 3, so it is 3 upon 1 plus 2. Is that right? Yes. Now if I try to just see this, it becomes 2 plus 6 plus 7 is nothing but what? 15 divided by 4 into 3. 1 plus 1 is 2, 2 squared is 4, so it becomes 4 into 3, which is equal to what? A by 2 plus b upon 1 plus 1 is 2, 2 squared is 4, so it becomes b by 4 plus 3 upon 3. 3 upon 3 is nothing but 1 only, right? Now, if I just keep it this way, that yes, it becomes 15 by 12, right? It is nothing but 15 by 12 equal to, now if I take that a by 2, right, plus b by 4 plus 1. Now what will I do here? Yes, I will take this 1 on the other side. What do I get then? A by 2 plus b by 4 is equal to 15 by 12 minus 1. 15 by 12 minus 1. What is 15 by 12? Yes, it is 3 4s are 12 and 3 5s are 15. It becomes 5 by 4 minus 1, which is equal to 5 by 4 minus 1 is equal to what? 5 minus 4 by 4. Yes, so now we have got this 5 minus 4 upon 4, which is what? Yes, which is 1 by 4. So you can say that a by 2 plus b by 4 is equal to 1 by 4, right? So now if I just keep this aside, if I take that 2 that side, if I take 1 by 2 common, I get a plus b by 2, which is equal to 1 by 4. Therefore a plus b by 2 is nothing but 1 by 2, right? So it becomes, therefore 2a plus b is equal to, if I it becomes 1 is equal to 1. So this is nothing but the second equation. Now if you see in first equation I only have a plus b equal to 2, and second equation I have 2a plus b equal to 1. So if I subtract 1 from 2, I mean 2 from 1, if I do 1 minus 2, equation 1 minus equation 2, what do I get then? A plus b equal to 2 minus second equation, 2a plus b equal to 1. So this becomes minus this is minus, right? School level mathematics divided by what? Yes, it becomes minus a, this becomes 0, minus a is equal to 2 minus 1 is 1, therefore we get a equal to minus 1. How to find b here? How to find b? We have seen that a plus b is equal to 2. So a plus b is equal to 2. That means what is a? Let me put a equal to minus 1, it becomes equal to 2. Therefore what is b? B you get b is equal to 1. So you have got the values of a, b and c, right? Let us simply substitute them. So you have got this a, b and c, right? You just keep them in mind. You have to need these values, right? A, b and c. Anyways, now let us represent it in a Jordan form. How to find a? How to find a? A is going to be what? Now see, if you see, there are two poles which are repeating or not? Yes. S plus 1 is the pole which is repeating 2 times. So minus 1 is repeating 2 times because the poles is what? S plus 1 equal to 0. Therefore S is equal to minus 1. Minus 1 comma minus 1. These are the two poles, right? Yes. Now the whole square. Yes. S is equal to minus 1 and minus 1 other two poles, and these two poles are repeating. So I need to have a separate section for repeating poles and for single pole, that is S plus 2. So let me have that. So yes, let me have compartments. One will be for the two poles and other will be for the single pole, right? So for two poles, if you see, I get it as minus 1, and here at the end I am going to write this third pole, which is S plus 2, which is nothing but S equal to minus 2. So here I am going to have minus 2, right? Now everywhere I am going to have zeros. Now see, because since this minus 1 has been repeated two times, I have to write 1 here. We have seen that, right? Jordan canonical form. We have to write 1 here. Now let us find B. If I find B is equal to what here? Yes. Let me extend this. Extend this green. This is B. For B, yes. Here I am going to have 1 because you have all ones, right? You have all ones. But yes, here already you have 1. You have 1. So that is the reason here I have to write 0. So this becomes B. We have seen that. Now, what about C? C will be having the partial fraction constants. What are those? Those are nothing but A, B, and C. So A is equal to minus 1, B is equal to 1, and C is equal to 3. So partial fraction constants is minus 1, 3, and 3. That is C. Now, what is D here? What is D here? We know that D is equal to B naught, but if you see here, degree of numerator is 2 and degree of denominator is 3, which means it is a strictly proper transfer function. The moment it is a strictly proper transfer function, it means that B naught is equal to 0. If B naught is equal to 0, then what? Matrix D is going to be 0. So at the end you get D equal to 0. So this is the state space representation of the transfer function shown in a Jordan canonical form. Now let us think of another numerical. Yes. So now x dot equal to 0 1 0 0 0 1 minus 2 minus 3 minus 4 0 0 3 y of t equal to 6 5 1, and what are they asking? They are asking us to find the transfer function. The transfer function is what? That is what they are asking. Don't you think that it is a controllable canonical form? You may say yes, but what I am saying is no. Why no? Let us see. See, for A matrix you always have 0 1 0, yes, 0 0 1, yes. These elements also agreed. But here in B matrix what you have is 0 0 and 1. In place of 3 you have 1. But here you have got 3, which means it is not in a controllable canonical form. Similarly, yes, you have this C matrix. I have no problem with it. But if you check out, because of this particular 3, I just cannot say that it is a controllable canonical form. So what will I do is this 3 is extra, right? And you know that this 3 is the gain. So what will I do is I will assume that it is a controllable canonical form, and then at the end I will just simply multiply by this 3, which is the gain. Is that okay? Yes, definitely, no problem. So let us simply do that. How to do that, sir? Let us find transfer function. So what is transfer function? Transfer function is going to be what? Yes. See, firstly let us think about the denominator. In case of denominators, we have seen that we have to go in a reverse order. We have to go in a reverse order. Reverse order, if you see, what do you get? The first one is nothing but minus 4, minus 3, and minus 2. And in controllable canonical form, we have seen that we have to change the signs as well. In case of denominator, we have to change the sign. So definitely here I am going to have s cube. Why s cube? Because it is 3 cross 3 matrix. No, right? It's a 3 cross 3 matrix. So yeah, definitely s cube will come. Now plus, what is the first element I am getting? minus 4. I have to change the sign, so it becomes 4s squared. Plus, what do I get next? Plus, I am going to have minus 3, so minus 3 becomes plus 3s. Plus, what do I have? It is minus 2. So minus 2 is going to become plus 2, right? This is the transform. Now, what about the numerator? Numerator, you have to just simply go in the reverse order without changing the sign. Without changing the sign. So it is going to become s squared is going to be the same. Plus, yes, reverse order, if you think of, yes, 5 will come and 6 will come. So it becomes s squared plus 5s plus 6. Is that correct? Yes, definitely. Why? Because if you see, what about s cube? S cube will be b naught into s cube, if you remember, and we know that b naught is 0. How you know that? Because D matrix is not given. D matrix has b naught, right? So this is how is a transfer function, but it is for a controllable canonical form. Ours, it is a controllable canonical form, but with gain 3. But with gain 3. So I should multiply 3 by 3 here. Now just imagine, just simply focus on this, right? If you did not multiply by 3, then you will get option A as the answer. See, no, s square plus 5s plus 6, and in the denominator you have got s cube plus 4s plus 3s plus 2. Same thing you have got. So if you had not multiplied by 3, then option A was the answer. But is it the answer? No. Why? Because 3 is the gain which has to be considered. So let us multiply by 3. So after multiplying by 3, the transfer function that we get is 3s squared plus 15s plus 6 divided by, denominator remains same, s cube plus 4s squared plus 3s plus 2, right? So it becomes 3s squared plus 15s plus 6. So where is the option? Yes, it is going to be option C. So option A is not the answer. This option A would have been the answer when here I had 1, but I don't have 1. There I have 3, so that 3, which is the gain, that has to be multiplied. So if I multiply that 3 gain, then I am going to get option C as the answer. Now, let us think of another question. Yes. So now, state equation for the state diagram has been shown below. Right. For a state diagram is shown below. You need to have the state space equation, that's it. That is what they are asking. The state equation for the state diagram given below is, now this is a state diagram. Now see, this is, if you see that, this is nothing but a signal flow graph, no, SFG. Yes, so this is a very interesting question. This is combination of SFG as well as our state space analysis. Now if you just see here, this term, this is R of S, this is X2 of S, this is C1 of S, this is also in C of S. Everything, if you see, everything, it is in frequency domain, no? Let me convert it into, what do you say, time. So if I say that, if I am going it in time, then just yes, this C of S becomes C of t, this C2 becomes C2, yes, this X1 of S becomes X1, and yes, definitely this particular, what do you say, this is X2, so this is nothing but X2 of S. Let me consider it is X2. Now this S inverse, what does this mean? S inverse means that here I am definitely having X2 dot. See here, in order to make you understand this concept, let me tell you. See, if for example you have X2, right? If for example you have X2 dot, if you apply Laplace transform here, right? If you apply Laplace transform, then yes, what will happen? It will be nothing but S into X2, right? You will get this X2 dot d by dt of X2 dot, and if you apply Laplace to it, what do you get? You get S into X2, right? Now, what if you divide this by S here? Then you will definitely get X2 dot only. Means 1 by S is the integration, no? See, let me show you some another example. Integration of 0 to t, if for example x has, this is f of t, or let us say x1, right? Yes, if I think of, let us say x1, right? If x1 has Laplace transform x1 of s, right? Now 0 to t integration 0 to t dt. What will be Laplace transform of this one? What will be Laplace transform of this one? Laplace transform of this one is going to be x1 of s upon s. Getting my point, right? Which means what? 1 by s is an integration term. So 1 by s, also called as s inverse. S inverse is what? Is nothing but an integrator, right? So the moment you integrate this x2 dot, you get x2. You get x2, right? Now let us try to find now here as well if you see. So this particular one, what does this become? Here you have got x1. So yes, this is going to become x1 dot, x1 dot, right? Now if you see at this particular node x1, at this node x1, what is happening at node x1? Let us see. At node x1 dot, this node, let me think of green. At node x1 dot, what is happening? One signal is coming from here, one signal is coming from here, and one signal is coming from here, which means all are incoming. So in SFG we have seen that if you want to write the node equations, how do you, so if it is x1 dot, then incoming is what? Yes, incoming is this one. x2 dot is incoming, x2 dot is incoming to this, plus means x2 dot plus again this c1 is incoming. C1 is actually what? This C1 is actually what? Z2 into x2. It is Z2 into x2. So yes, x2 dot is coming, x2 dot is incoming, plus x2 into z2 is also incoming because this is x2. So this is x2 into z2 will give you this. So plus x2 into z2 is also coming, right? And next is what? Next is what? Next is minus p1. Minus p1 is also coming. So x1 into minus p1 is also coming. So it is minus p1 into x1. So whatever are incoming to this node x1, that is what we are supposed to consider. So let me call this as equation 1. Now let us think of what is happening at node x2 dot. At node x2 dot, where is that? This is the node x2 dot. At x2 dot, this is incoming and this one is incoming. So this is incoming. This is going to be, this is r. In small letter it becomes r in time domain. So it becomes r into a, right? So here I have x2 dot equal to incoming signals are what? Ra, right? Minus Ra minus P2 into what is this signal? This is nothing but x2 minus P2 into x2 minus P2 into x2. This is nothing but the second equation, right? Now x2 dot is already there. Now you please put this 2 in 1, right? You please put this 2 in 1. What do you get then? You will get x1 dot. So put 2 in 1 such that you will get x1 dot, because in x1 dot equation you are also having x2 dot, right? So if you put 2 in 1, then yes, that x2 dot will get eliminated. So x1 dot is equal to, in place of x2 dot you have to put this equation, right? So it becomes Ra minus P2 x2, right? Ra minus P2 x2 plus x2 z2 minus P1 x1, right? So if you think of this x2 terms, these two are common. So let me consider x2 outside. So inside I can write as z2 minus p2. So it becomes z2 minus p2. Is that right? Yes. Now these two terms are over. Now Ra is there and minus p1 x1 is there. So it becomes minus p1 x1 plus r into a. R into a. Let me call this as equation 4. This is x1 dot. So x1 dot I have got. Complete x1 dot is here. Similarly, x2 dot is also here. So state equation can be formed. But output equation why? Yes, let us think of that first. So this is the output. Output here they are saying is this C, right? So if you see here, this node is nothing but this node. So at this node, if you see, this signal is coming, and what is coming? This signal is coming. So at here, what is going to happen? This is Z1. So Z1 into 1, Z1 into X1. This is X1. So Z1 into X1 is coming, and this is also coming. So Y is equal to Z1 X1 plus what else is coming? X1 dot is coming from here. So plus X1 dot. Is that correct? Yes. Now you please put equation 1, or rather let me call this as equation 3. You please put 3 and let me call this as 4. So let me put 3 in 4, which means, see here you have got this x1 dot, right? You have to eliminate this x1 dot. So in order to eliminate that, let me put this equation 3, which is of x1 dot equation, let me put it in 4. So I will get what? I will get y equal to z1 x1 plus x1 dot. What is x1 dot? Z2 minus P2 into x2 minus P1 into x1 plus RA. This is equation 5. Now you have got both the state equations and you have got this output equation also. You please represent them in terms of a state model. How do you do that? Just simply this way. You get A matrix as what? See, A matrix will be what? Dependency of x1, right? Let us think of x1 dot first. Is there dependency on x1 here? Dependency on x1 here? Yes. Minus P2. So the first term is going to be minus P2. The next is what? Dependency on x2, because here I am going to have x1 and x2 only, right? Yes. Now next is what? Dependency on x2. Dependency on x2 is z2 minus p2. So it goes z2 minus p2. Similarly, what about x2 dot here? Yes, x2 dot is here. Is there any dependency on x1? No, x1 term is not there. So it is going to become 0. Similarly, dependency on x2, yes, minus p2. Definitely minus p2 is going to be there. By the way, this is minus p1. This is minus p1. Why? Because you have got this x1. So here minus p1 was there. Minus p1 was there. Right? We know that. Now, so this becomes your A. What about B? What about B? Is there any dependency of input on A? See, in x1 dot, if you see, is there any dependency of input? Because R is the input, right? R is the input. So yes, definitely it is A into the input. Similarly for x2 dot also, it is A into this R. So here both ways I am going to get AA. Similarly, what about C here? Yes, C is going to be what? Output equation. Is there dependency on x1? Yes, z1 is there. Then for x2, z2 minus p2 is there. So, and similarly, if you think of x1, yes, here I am going to have minus p1 also. So it becomes z1 minus p1 because it is x1 only, no? Common. So y becomes z1 x1 minus p1 x1. So it is z1 minus p1 into x1, right? And here I am going to have x2, so it becomes z2 minus p2. Z2 minus p2. Now, what is D matrix? What is D matrix? Is there D matrix? D into U, right? So yes, you have this R into A, so which means A is will be the element in the D matrix. So it is going to be A. So the state space model for that particular SFG has been formed. This is the way we have done it. Yes. Now let us think of another question. Yes. So now the state transition matrix of the system with the transfer function g of s equal to 1 upon s square is what? That is what they are asking. They are asking basically the state transition matrix, and they have not at all given you the system matrix A. They have only given you the transfer function. So from the transfer function itself, you are supposed to find the A matrix as well. So let us see how to do that. Yes. So from this, if you see g of s equal to 1 upon s square, yes. Let me write g of s equal to 1 upon s square. Right. This is nothing but y of s upon u of s. Yes, definitely, no problem. Now, see here. What do you mean by this? If I take this u of s here, u of s is going to be s squared into y of s, right? What does that mean? If I take it in terms of time domain, then it becomes u of t, which is equal to s squared into y of s. It indicates that it is going to be double derivative, so it is y double dot. Therefore, I can say that it is nothing but d2y by dt squared equal to u of t. Right, definitely. Now, how to do that? If you remember, in our derivation in finding the controllable canonical form, we have seen that we can take output as the first variable. So let me take output as the first variable. Means output is y, right? So let me take first variable as output, which is x1. Now, if I differentiate x1, then if I differentiate x1, means x1 dot is equal to what? X1 dot is equal to x2. Let me consider another variable. Now let me consider x2 dot, then what is x2 dot? X2 dot is equal to what? Yes, x2 dot is nothing but x1 double dot. What is x1? X1 is nothing but y, so it becomes y double dot. So yes, got the answer. And we know that y double dot is nothing but u. So you understand that x1 dot is equal to x2 is one equation, x2 dot equal to u is another equation, and y equal to x1 is another equation. From this, definitely you can have those A matrix easily. It can be formed. So yes, what is A matrix here? A matrix is going to be yes. It is going to, because is there any dependency of x1 dot? If you see, is there a dependency on x1? No. So here 0 will be there. Is there dependency on x2? Yes, dependency on x2 is there. So here definitely I will get 1. Similarly, if you think of x2 dot is what? Yes, x2 dot is going to be, is there any dependency on x1 and x2? No. So it becomes 0, 0. That's it. This is our system matrix A. I hope it is clear. Even if you don't understand, you may say that, sir, but how you get this A matrix directly? If you don't understand, no, just simply do it slowly, slowly. See, if you know that, what is x dot equal to x dot, you have the x1 dot and x2 dot, right? And it is equal to this A matrix into x1 and x2, right? If I want to find this x1 dot, then x1 dot is going to be what? This into this x1 plus this element into this x2. So yes, you tell me, in x1 dot you have only x2. No, x1 is not there, so definitely this has to be 0. And yes, x2 is there. Yes, x2, with that what you have? You have 1, so here there has to be 1. Similarly, in case of x2, if you see x2 dot, if you see x2 dot, then in x2 dot you have only you don't have any dependency on x1 and x2, which means here it is going to be 0, so it is going to be 0 1 0 0. That's it, very simple. Now let us take inverse Laplace transform approach and try to solve it. Very simple, because e to the power at has to be found out, right? So it is going to be very easy question. So yes, by inverse Laplace transform approach, or you can say method, what do we get then? We get that si minus a inverse Laplace inverse of si minus a, it is nothing but e to the power at, which is nothing but stm, we have already seen, right? Now what is si minus a? Let us find si minus a first. Si minus a is equal to what? S 0 0 s, right? Minus a, what is a? A is nothing but 0 1 0 0, so 0, so 0 1 0 0. What do you get here? You get s minus 1 0 and s, right? Now you need to find inverse, so si minus a inverse. What is that inverse? Inverse is going to be what? Yes, definitely adjoint of a upon determinant of a. So for adjoint, what you do is flip the principal diagonal element, so it becomes s and s, and you just change the sign of remaining. So this 0 remains 0, and this minus 1 will become plus 1. That's it. And divided by determinant. What is the determinant of this? Determinant is nothing but what? This into this minus this into this. So determinant is going to be s squared 1 by s squared, right? Now let us find that. So let us find Laplace inverse. So if I try to find Laplace inverse of the same, what do I get then? Because see, what will I do first for to find Laplace inverse? No, I will firstly keep this s squared inside. So it becomes s upon s squared. So it becomes 1 by s. 1 upon s squared. If I shift this as 0, it becomes 0 and it becomes s upon s squared. S upon s squared is nothing but 1 upon s. Getting my point, right? So now Laplace inverse. What is that Laplace inverse? Laplace inverse is what? 1 by s Laplace inverse is 1. 1 upon s squared Laplace inverse is t. 0 Laplace inverse is 0 and 1 by s Laplace inverse is 1. So this is your e raised to at. This is your e raised to at. So this is STM, which is what? 1t01. So sorry, in this option there is 1. So sorry, this option we have 1, right? I'm so sorry. This was 1. So out of them, yes, what is the answer? What is the answer? 1t01 is the answer. That's it. Very simple question, right? So in this way, we have seen some sums as well on the state space analysis. Yes, now after this, immediately we will be taking some extra sums as well related to state space and related to stability as well, related to controllability, observability, and all. Everything we will take, but at the end. So stay tuned. Thank you.